In this lecture, we're going to continue talking about trigonometry, and we're going to talk about the sum and difference formulas. So we'll start by presenting what the sum and difference formulas are, and then we'll do some examples where we're going to practice working with them. So let's start with the sum and difference formulas for cosine. We have that the cosine of the sum of two angles, alpha and beta, is equal to cosine alpha times cosine beta minus sine alpha sine beta, and the cosine of the difference of two angles, alpha minus beta, equals cosine alpha cosine beta plus sine alpha sine beta. Next we have the sum and difference formulas for sine. Sine of the sum of two angles, alpha plus beta, will be the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta, and the sine of the difference of two angles, alpha minus beta, will be sine of alpha cosine beta minus cosine alpha sine beta. You might want to take a minute and copy these down onto a sheet of paper, or make sure that you have a sheet that has them on it so that you can easily refer to them as we work through our examples. And finally, the sum and difference formulas for tangent are as follows. The tangent of the sum of two angles, alpha and beta, will be tangent of alpha plus the tangent of beta divided by 1 minus the tangent of alpha times the tangent of beta. And the tangent of the difference, alpha minus beta, will be the tangent of alpha minus the tangent of beta divided by 1 plus the tangent of alpha times the tangent of beta. So let's look at a few examples. For our first example, we want to find the exact value of the function sine of 5 pi over 12. Now remember, when it says exact value, that means they want you to leave the radicals however they may be. Don't put it in your calculator and approximate it. So the first thing that we need to do in order to use the sum or difference formulas is find two angles that are on our unit circle whose sum or difference equals the angle that we're looking for. So if I start with our basic angles, pi over 6, pi over 4, and pi over 3, and write all of them with the common denominator of 12, which is the denominator we're looking for, pi over 6 would be 2 pi over 12, pi over 4 would be 3 pi over 12, and pi over 3 would be 4 pi over 12. Now, if we couldn't make 5 pi out of 12 out of a combination of these three angles, we would look at additional angles on the unit circle. But we could make 5 pi over 12 by adding 2 pi over 12 plus 3 pi over 12. So we're going to use pi over 6 and pi over 4. So again, we can rewrite 5 pi over 12 as 2 pi over 12 plus 3 pi over 12. So we have the sine of 2 pi over 12 plus 3 pi over 12, which essentially is the sine of pi over 6 plus pi over 4. And so if we look at the formulas that we have for the sum or difference formulas, we're going to use the sum formula for the sine function. So our alpha is pi over 6 and our beta is pi over 4. If we apply the sum formula for sine, we're going to have sine of pi over 6 times the cosine of pi over 4 plus the cosine of pi over 6 times the sine of pi over 4. And we can evaluate each of those using our unit circle. Sine of pi over 6 is 1/2, and the cosine of pi over 4 is root 2 over 2. The cosine of pi over 6 is root 3 over 2, and the sine of pi over 4 is root 2 over 2. So we have 1/2 times root 2 over 2 plus root 3 over 2 times root 2 over 2. If we simplify by multiplying them together and then add our fractions together, we're going to wind up with the square root of 2 plus the square root of 6 all over 4. Let's look at another example where we want to find the exact value. This time we want to do the tangent of 195 degrees. Now again, what we want to do is we want to find two angles on our unit circle that we can combine by adding or subtracting that will give us this angle we're looking for. So it's a little bit easier with degrees because we don't have to deal with fractions. We can rewrite 195 as 225 minus 30. So we're looking at the tangent of 225 degrees minus 30 degrees. We'll apply the difference formula for tangent, so tangent of alpha minus beta equals the tangent of alpha minus the tangent of beta divided by 1 plus the tangent of alpha times the tangent of beta, where alpha is 225 and beta is 30. And so that'll give us the tangent of 225 minus the tangent of 30 divided by 1 plus the tangent of 225 times the tangent of 30. We'll take a minute and figure out what these tangent values are using our unit circle. So remember, tangent of 225 will be sine of 225 over cosine of 225. Using our unit circle, we see that sine of 225 is negative root 2 over 2, and cosine of 225 is also negative root 2 over 2. So if we simplify that, the tangent of 225 will be equal to 1. Now we're going to go through the same process to find the tangent of 30. The tangent of 30 will be sine of 30 divided by cosine of 30. The sine of 30 is 1/2, and the cosine of 30 is root 3 over 2. If we divide that out, the 2's will cancel out. We'll be left with 1 divided by the square root of 3, which we can rationalize by multiplying both numerator and denominator by root 3, and that's going to give us that the tangent of 30 is root 3 over 3. So if we plug those values into our formula, we're going to get 1 minus root 3 over 3 divided by 1 plus 1 times the square root of 3 over 3. But we want to rationalize our denominator to get rid of the square root sign, so we're going to multiply both numerator and denominator by the conjugate of the denominator, which is 1 minus the square root of 3 over 3. If we multiply that out in the numerator using the FOIL method, we're going to get 1 minus root 3 over 3 minus root 3 over 3 plus 1/3. And in the denominator, we'll get 1 plus root 3 over 3 minus root 3 over 3 minus 1/3. If we get everything over a common denominator of 3 and combine, our numerator will simplify to be 4 minus 2 times the square root of 3 over 3, and our denominator will be 2 over 3. When we divide those fractions out, the 3's will cancel out, leaving us with 4 minus 2 root 3 over 2, which will simplify to give us 2 minus the square root of 3. Now here's a different kind of example where we want to find the exact value. This time we're given the sine of 20 degrees times the cosine of 80 degrees minus the cosine of 20 degrees times the sine of 80 degrees. And so what we need to do is we need to match what we're given here up with one of the formulas from the beginning of the lecture. So the problem that we were given matches up with the formula for the difference formula for sine. Sine of alpha minus beta equals sine of alpha times cosine beta minus cosine alpha times sine beta. Our alpha value will be 20 and our beta value will be 80. So using that difference formula, we can rewrite our problem as the sine of 20 degrees minus 80 degrees. If we simplify, that'll be the sine of negative 60 degrees. But negative 60 is not going to be on our unit circle, so we want to find a coterminal angle. So to find our coterminal angle, we're going to add 360 degrees to our angle of negative 60. So negative 60 degrees plus 360 gives us a coterminal angle of 300 degrees. And so the sine of negative 60 will be the same as the sine of 300, which, using our unit circle, appears to be negative root 3 over 2. Here's another example where we want to find the exact value. The cosine of 5 pi over 12 times the cosine of 7 pi over 12 minus the sine of 5 pi over 12 times the sine of 7 pi over 12. Take a couple minutes and see if you can simplify this one by yourself. If you finish or get stuck, feel free to follow along with me when you continue your lecture. So the first thing we need to do is identify which formula we're going to use, and it looks like this is going to be the sum formula for cosine. Cosine of alpha plus beta equals the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So using that sum formula, we can rewrite our problem as the cosine of 5 pi over 12 plus 7 pi over 12. If we add the angle measures together, 5 pi over 12 plus 7 pi over 12 will give us 12 pi over 12. So we have the cosine of 12 pi over 12. And the 12 will cancel out from the numerator and denominator, leaving us with the cosine of pi, which we know is going to be negative 1. So the cosine of 5 pi over 12 times the cosine of 7 pi over 12 minus the sine of 5 pi over 12 times the sine of 7 pi over 12 will equal negative 1. And the last thing that we want to be able to do in this section is establish an identity using these sum and difference formulas. So for example, we want to show that the cosine of 3 pi over 12 plus theta equals the sine of theta. We're going to start with the left-hand side of the equation, cosine of 3 pi over 2 plus theta. We can simplify this using the sum formula for cosine. So cosine of alpha plus beta equals the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. For our problem, alpha will be 3 pi over 2 and beta will just be theta. So if we apply the formula, we can rewrite our problem as the cosine of 3 pi over 2 times the cosine of theta minus the sine of 3 pi over 2 times the sine of theta. 3 pi over 2 is one of the angles on our unit circle, so we can evaluate that cosine and sine. The cosine of 3 pi over 2 is equal to 0, and the sine of 3 pi of 2 is equal to -1, so we'll get 0 times the cosine of theta minus a -1 times the sine of theta. If we simplify that, the first term will go away, and the -1 becomes a positive, so we'll be left with sine of theta, which is what we were trying to show. So this establishes the identity. Let's do another problem where we want to establish the identity. So this time we have the cosine of alpha plus beta divided by the cosine of alpha minus beta equals 1 minus the tangent of alpha times the tangent of beta divided by 1 plus the tangent of alpha times the tangent of beta. So we'll start with the left-hand side, cosine of alpha plus beta divided by the cosine of alpha minus beta. Now this is the sum formula for cosine and the difference for cosine, respectively, so we can apply those formulas and rewrite our problem as the cosine of alpha cosine of beta minus sine alpha sine beta all over the cosine of alpha cosine of beta plus the sine of alpha sine of beta. Now, our goal is to get the right-hand side of the equation up at the top. And notice that the first term in both the numerator and denominator of that is equal to 1. So if I wanted to make the first term here a 1, I would divide by the cosine of alpha cosine of beta. So let's do that. Let's factor out a cosine alpha cosine beta from both our numerator and denominator. If I factor out a cosine alpha cosine beta from both the numerator and denominator, I'll get the cosine alpha cosine beta times 1 minus the sine alpha sine beta over cosine alpha cosine beta divided by the cosine alpha cosine beta times 1 plus the sine alpha sine beta over cosine alpha cosine beta. Now, since sine over cosine is equal to tangent, we can rewrite that as cosine alpha cosine beta times 1 minus tangent alpha tangent beta, all divided by cosine alpha cosine beta times 1 plus tangent alpha tangent beta. The cosine alpha cosine beta that's in the numerator and denominator will cancel each other out, leaving us with 1 minus tangent alpha tangent beta divided by 1 plus tangent alpha tangent beta, which is what we were trying to show. So we've established this identity.